Okay, hi everyone. This is a joint work between Jing, a graduate student at Shenzhen University, and Professors Weike and Zhong. This work investigates state sparsity in multi-behavior sequential accommodation and proposes a generic behavior-aware data augmentation framework to address this problem. First, we give the problem definition of multi-behavior sequential accommodation. For each user view, the input is a sequence of its interactions with items, while each table in the sequence contains the item that user U has interacted with at the current timestamp and the corresponding behavior. Our goal is to predict the item that user U is most likely to purchase at the next timestamp. Next, let's see some data augmentation methods to address the data sparsity problem. Overall, these approaches can be categorized into three classes. The first category uses contrastive learning to enhance training samples, among which the most typical models are CL4S-RAG and DORAG. In addition, there is a class of models that extend the original sequence by some pre-training methods, while RSS considers that each item in the sequence should be possible to be sampled as a target item and designs a recency-based sampling strategy to generate some different new samples. Despite the effectiveness of these data augmentation methods, there are still some limitations. Firstly, these methods only focus on a single type of behavior, neglecting the correlations between multi-type behaviors in user-item interactions. Second, enhancing training samples with some pre-trained models often relies on a specific network architecture, which makes it challenging to seamlessly transform to other network structures. In addition, models like S3-RAG rely on some additional auxiliary information that cannot be adequately supported by limited data. To overcome these limitations, we propose a novel multi-behavior data augmentation model for sequential accommodation, namely MBASR for short. This is the first data augmentation method specifically tailored to solve the sparsity problem in MBSR. We propose three behavior-aware data augmentation methods, including order perturbation, redundancy reduction, and pairwise swapping to generate new sequences. These methods can be seamlessly integrated into wireless existing MBSR models to boost their performance. Moreover, we design a position-based sampling strategy that can maximally preserve the smooth sequentially between neighboring items in the original sequences. Here, we show the overall architecture of our proposed model. The basic idea of our MBASR is to design different behavior-aware data augmentation operations to generate rich training samples that provide insights into users' dynamic preferences, which can apply to wireless downstream tasks. First, we take the purchase behavior as the boundary to divide the original sequence into multiple subsequences. Each purchase and click behaviors between two consecutive purchases can be regarded as a user's short-term reference within a specific period. Then, we hypothesize that items closer to the current position will inherently align more with the present user's preference, and therefore exert a more substantial influence on a downstream task. As a result, we design a sampling strategy aimed at on the order of item positions. With item close to the current position, assign a lower probability of being sampled. In the augmenter, we design three behavior-aware data augmentation operations, including subsequence order perturbation, subsequence redundancy reduction, and pairwise subsequence swapping. First, it is observed that users often click a series of similar items before making a purchase. Due to the existence of item similarity, these click behaviors do not strictly adhere to a specific order, and the correlations between successive clicked items are not particularly strong. Based on this observation, we propose to inject punctured order perturbations into the clicked items within subsequences to introduce diverse sequential patterns. First, for each user, we calculate the sampling probability of each subsequence based on the sampling function defined earlier, and sample a subsequence based on this sampling probability. And then we introduce an appropriate order perturbation into the subsequence. Then we again use the same sampling function to calculate the sampling probability of each clicked item in the subsequence to keep the operation simple. And we order the clicked items in the subsequence based on this probability. For each user interaction sequence, we repeat the above operation NOP times so that we can obtain the augmented complete sequence. The second augmentation operation is redundancy reduction. When users click items in a short period, similarities or redundancies will inevitably occur. For example, users may explore several similar features before making a final purchase decision. So, we believe that user representations can be enhanced by mitigating redundancy. In pursuit of this, we choose the simple operation of deleting the specific click item. Similar to order perturbation, we first compute the sample probability of each subsequence being sampled based on its position. Sample a particular subsequence based on this sample probability, and then sample a click item in that subsequence for deletion in the same way. Repeat the above operation NRR times to finally obtain the augmented sequence. By randomly removing some similar or redundant items, we can simulate the randomness and the diversity inherent in a user's decision-making process. We also design an augmentation operation that occurs between subsequence called subsequence swapping. As we mentioned before, a subsequence categorizes a user's interest during a specific period. So, we take it as the smallest unit, allowing for moderate shuffling of the order between subsequences. Specifically, we first randomly select a source subsequence and obtain its index. Next, we design a sampling probability based on the position awareness of the source subsequence to minimize noise amplification during the swap operation process. Subsequence close to the source subsequence have a higher probability of being sampled at the destination subsequence. Once the source subsequence and the destination subsequence are identified, we enhance the original sequence by swapping these two subsequences, resulting in the augmented sequence. In the experimental part, we answer the following 4 research questions. We conduct experiments on 3 public recommendation datasets, including Tmall, UB, and Jingdong, which are all related to e-commerce. For these datasets, we only keep the clicks and purchase, and perform some pre-processing on them. We discard the cold start items, the cold start users, and only keep the first user item behavior trigger for repeated once in a sequence. In each dataset, we take the last purchase as the test step, the penultimate purchase as the validation step, and the rest as the training step. Moreover, to simulate the sparsity of the data, we take a portion of items at equal intervals in each user's interaction sequence for training. The statistics of the processed dataset are shown in the table. For the evaluation metrics, we choose HR and NDCG, where HR emphasized the accuracy of the model and NDCG emphasized the ranking of the items. To showcase the effectiveness of our MBASR, we integrate it into a wide range of representative models, including some RN-based, attention-based, GNN-based models for multi-behavior sequential recommendation. Moreover, we compare the boosted performance with the very state-of-the-art data augmentation method, RSS, as it is a data-oriented augmentation method like our MBASR, which guarantees fairness in the experiments. The table shows the experimental results of different MBASR models with or without our MBASR on the 3 datasets. From the table, we can clearly observe that our MBASR gives significant improvement to a wide range of mainstream MBASR models on all datasets, which demonstrates the superiority and applicability of our MBASR.
Excuse me, Jing Xiao. We only have 3 minutes left. Okay, thank you. You can continue. Yeah, only 3 minutes left. You can continue. Yeah.
To show the superiority of our MBASR, we compare it with the state-of-the-art data augmentation model RSS. Specifically, we use SASREC and SASBAR as the backbone models, evaluating the performance improvement brought by RSS in our MBASR from the perspectives of single behavior sequential recommendation and multi-behavior sequential recommendation, respectively. Our MBASR consistently beats RSS on almost all these stats and shows significant performance improvement. To comprehensively validate the contributions of different data augmentation operations, we illustrate the performance of models when combining other 2 data augmentation operations. As can be seen, each proposed data augmentation method brings varying degrees of performance improvement in all downstream tasks. To investigate the impact of data sparsity on our MBASR, we intentionally inject sparsity into UB by extract items from each user sequence at varying intervals. In the figure, we show the HR at 10 results of our MBASR with SASBAR as the backbone model when using the 3 different data augmentation operations on these 3 datasets. The results indicate a progressively poor performance on HR at 10 as the data sparsity increases, while MBASR can always enhance the original model's performance with its 3 data augmentation operations. Overall, this work studies an important issue in MBASR, problem of data sparsity. To address this problem, we propose a generic data-oriented framework named MBASR. It can be seamlessly integrated into wireless downstream models and significantly improve their performance. In addition, we design a position-based sampling strategy which can reduce the level of noise and enable a trade-off between enriching the samples and preserving the original information. Extensive experiments also demonstrate the detailability and validity of our model. Thank you. If you have any questions, please feel free to contact me.
Okay. Let's thank the speaker and for Zhu for being a part.